Okay, so in this lecture, first I'm going to introduce some more interpolation techniques for estimating fluxes as a function of cell average values. And then after that, we will start the next topic, and this topic, the finite volume topic, will be finished. And then after that, we will start stability for space-time problems. Okay. So let me get started. So the last topic was a generic one-dimensional finite volume method that we learned how to approach these problems. And now I want to start with more on interpolations to obtain fluxes as a function of cell averaged values. Okay, so this is a topic that we want to talk today, and I'm gonna introduce two schemes. The first one is Upwind interpolation scheme, or UDS, for convective fluxes. Okay, so let's see how this interpolation works. It's a simple interpolation, but it's pretty common and useful. So let's see the domain that we have. So let me do it this way with so we have these two, and then I need one more here. Why it's not working here? Okay, so let's see the domain that we have. So say we have this main point here, P, and then here we have the east grid shown as E, and then here we have the west grid shown as W. And then we want to approximate this flux that goes here as E. Okay. So in the upwind scheme, we say phi E equals to, this flux equals to, very simply, to the value of phi or phi at point P if V dot N at E is greater than 0. What does this mean? This means that the flow is going from left to right. So this is going from here to here. So V dot N, V is this vector, and N is this vector. So this is positive, okay? And if V dot N is negative, that means we have a flow that is coming from right to left, then the value of phi E is going to be phi at point E. And what does that mean? That means we have a flow that is going this way, so this is vector V, and then N is this way. So V dot N is going to be negative. So the value of flux at E here is going to be, we just set it as the downstream, this value here, the upstream value. So this is E, right? So we set it like the E is here, it's going to be just this value here. And the other way around, when V is this way, we have a flow that is going from left to right. We just say this E here is just the value at the value of phi at point P. Okay, very simple approximation, but it is very useful because it is never oscillatory. But the only disadvantage of that is it is numerically diffusive or dissipative. And what does that mean? That means that if you use this interpolation, you will have some numerical diffusion. And what I mean by numerical diffusion means a virtual, an artifact diffusion that is not really in your physical equations. It is an artifact of the discretization and using this method. So when you use this method, it's gonna produce some numerical diffusion that you might see in your solutions that do not really exist. So let's see that. So if you have a Taylor expansion, and you can find that numerical diffusion by this Taylor expansion about point xp, then phi E is gonna be phi at P plus, so I want to see what is the leading error of that, is gonna be x at E minus x at P partial phi over partial x at point P plus xe minus xp square over 2 factorial partial phi over partial x square at point P plus other terms, right? So as you see, this is going to be our leading error. And so this approximation is order delta x, right? As you see, this is delta x. So this approximation is going to be order delta x. Okay. So this was to find the order of accuracy of this approximation. The order delta x is never oscillatory, but it's kind of numerically diffusive. So let me talk about another approach, which is a higher order method. So this was order delta x, and now we want to go to a higher order method. And this one is called quadratic upwind interpolation or quick. So this is approximation by quadratic profile between two nearest nodes. Okay, so let's see how this works. It's a higher order one. So let me do it here. So we are gonna use more nodes. Okay, so the first point here is P. This point is E. This point is EE. This point is west. And this point is west-west. Okay? And we want to approximate this flux here, E, and interpolate that based on the nodal values. So I'm gonna, because this is a higher order one, we are gonna use more nodes. And what we are gonna do, we approximate a quadratic profile between two nearest nodes here, and we fit that to get this interpolation. So phi at E is represented at phi at U plus G1 phi at D, and what I mean by D, it means downstream. First downstream node, and then second one is gonna be first phi U, first upstream node, and then G2 phi U minus phi UU. Okay. So let me just define this. This is gonna be first upstream. This is first downstream, and this is second upstream. Okay. So if flow goes from P to E, that is left to right, then the upstream is going to be W, upstream is going to be P, and downstream is going to be E, right? How? This is going to be the first upstream. If you have this flow in this direction, then this is going to be first upstream. This is going to be the second upstream. And then this is going to be the first downstream term, right? So we just substitute, instead of phi U, you can write phi P. instead of phi d, you can write phi e, and instead of phi uu, you can write phi w. And then this will be your approximation. And we'll talk about G1 and G2. Those are just two coefficients. Okay. But on the other hand, if flow goes from E to P, that means it is a right to left flow, then our second upstream value will be EE. First upstream value is going to be E, and first downstream value will become P. How is that? Say you have a flow in this direction. This is going to be first upstream value, this is going to be the second upstream value, and this is going to be the first downstream value. Okay, so instead of a UU, instead of you want to write phi E. Instead of D, you want to write phi P, and instead of UU, you will write phi EE. So this is how you should treat this problem, depending on the flow direction. And now I want to just introduce these G1 and G2. What are those coefficients? So G1 is XE minus XU, XE minus XUU over XD minus XU, XD minus XUU. And G2 is XE minus XU, XD minus XE over XU minus XUU, XD minus XUU. So these are just how these coefficients can be found. And for uniform grids, it's a kind of simpler approximation. So for uniform grids, we have phi E equals to 6 over 8 phi U plus 3 over 8 phi D minus 1 over 8 phi UU minus 3 delta x cube over 48 partial phi over partial x cube evaluated at U. And as you see, this is order delta x cube. So it is higher order approximation compared to the other one, which was order delta x, right? So as you see, and you noticed, higher order schemes use more nodes and become more complex. As you see, we use more nodes now. We used 3 nodes and possibly 4 because of the depending on the direction of flow, and it is more complex, as you see here, right? It is more complex. Phi u plus 3 over 8, okay? So it is more complex than first order method, which is here. So it is third order, higher order, but it's more complex. So these were 2 interpolation schemes that you would need when you want to approximate the flux at the boundaries, at these cell average boundaries right here, right? And you can use those as well. And these are 2 famous ones that you might hear when you work with these finite volume methods. One is called Upwind method, and the other one is called Quick method, quadratic upwind interpolation, especially if you want to, if you work with some of these finite volume codes, okay? So this was just a brief overview of finite volume methods. So you see another method for solving partial differential equations. So the most commonly used one is the one that we worked most, which is finite difference method. This finite volume method is mostly used for fluid mechanics, fluid dynamics, water flows, air flows, approximations, and we have also another method which is called finite element method, which I'm not going to go through it in this course, and that is mostly for structural engineers where they have more linear equations, and that's also a very well-established method for approximating these and solving these partial differential equations. Okay, so in the next lecture we are going to start stability for space-time problems.